not going to be getting a test on chapter 6. However, what I am going to be doing, kind of like we've done, I think we did it for integrations, net change, we did it for slope fields. I didn't just have you guys doing WebAssign, I also had a behind the scenes CalcAB. I'm going to have something similar for areas and volumes, especially because, once again, I think visualization is key to actually solidifying your understanding. And there's only so much I can do in class. I want us to be getting into WebAssign and you guys practicing problems before we leave every day. But to be able to do that, I'm not going to be able to give you as much content or as many examples as I would like, especially with the time limits put upon us. So therefore, I am going to be not forcing you to watch all the videos. I'm not assigning the videos, but they would be good. Instead, I'm going to be assigning practice, okay? Instead of assigning like lots of individual, I'll probably be assigning instead, there's like a quiz at the end of the area, a CalcAB quiz, and then there's also a CalcAB quiz at the end of the volume. Wherever it is. A quiz at the end of the volume. I'll probably just be assigning those, but I wanted to take another quick peek before I just haphazardly did it. Because I want to make sure that this is useful to you. Not that you guys have to be getting necessarily 100%, but 0s, 25s, 50% won't get you full credit. You do need to be like passing the cons. You might have to do it a couple times to pass it. But I think it gives you like a live, you're getting it, or a live, you're not getting it. Let's get some extra content. Does that make sense? Okay.
When is that?
That's just going to be due next Thursday. I'm just going to assign one CalcAB that you're just playing with over the next week or so as you're doing WebAssign. Is that cool? Okay. So let's go ahead and get into notes. And notes start off in a way that hopefully isn't too hard because how do we find area? An integral. That's what area has always been found by, right? But what area do you find when you integrate? What area do you find when you integrate? Area underneath a curve, between the curve and the what? So let me use, let's see, did you guys figure out that the green is x squared and the red is square root of x? So we have y is equal to x squared, that's this guy right here. And then we have y is equal to square root of x. That's this guy right here. If I was to write right here, the integral of square root of x dx, question, what area would I be talking about? Hold on, first of all, does anybody know what bounds I would be using? What is naturally sectioning off this portion, this area that they're wanting?
Negative numbers.
No, no negative numbers.
0 to 2.
0 to, not 2. 0 to 1. Why is it 0 to 1? If I plug in 0, what's 0 squared? 0. What's the square root of 0? 0. Oh, it's an intersection point. It's a point that's a solution to both equations. Hey, what's going on at 1? What's 1 squared? Yeah, 1 squared is 1. What's the square root of 1? 1. So if I was to set x squared equal to square root of x, when will these intersect? When will they be equal to each other? When will their points be shared? I would probably do some sort of squaring of both sides. I would get x to the 4th equals x. I would then subtract, because factoring is key to getting all intersections. This would lead me to x cubed minus 1 times x is equal to 0. I know you see it on the picture, but the algebra would also lead you to 2 intersection points of 0 and 1, right? These are called natural bounds because it's natural to the curves. They bound each other. They intersect each other. They have this nice little shared area. Okay, so my bounds would be 0 and 1. But what area would I be shading if I was just using square root of x? Under square root of x, right? So I would just be talking about this guy. But is that the area that I want? No. I want the blue. But hold on, how can I get the blue? Well, I can take what's underneath the square root of x and I can subtract what's underneath what? X squared. Because if I'm talking about x squared, wouldn't I be finding the area under his curve? Right? So if I take what's under the red and if I subtract what's under the green, what am I going to get? The area between. I'm going to get the area between.
Isn't that just FTC?
Well, it's putting two FTCs together. Does that make sense? Because I'm taking one curve, and that's okay, that was a little intense, but we're good, we're good. I'm taking one curve and saying, let's go underneath that, and I'm taking another curve and saying, let's go underneath that, and let's subtract the two. Now, what we also saw was these natural intersection points. To find them, all we have to do down here is just set the curves equal to each other. If they don't give us like an A and a B, if they don't give us like a beginning and an ending, we're like, fine, we're just going to do it ourselves. And doing it ourselves says set them equal to each other and solve, kind of like we did right here. Some nice algebra stuff. And then if they say defined, it's like, okay, cool, they're telling me A, they're telling me B. So if they tell me A, then they're saying cut it here. If they're telling me B, they're saying cut it here. There's nothing special about those points. They're not intersections. They're just saying, I don't know, whatever, just find that area between. But do you guys know why, for this one, I would have to do the integral from A to B? I don't know what the numbers are, whatever, they tell them. Why am I going to have to do F minus G? Why couldn't I do G minus F? Why do I need to do F minus G and not G minus F? What's true about F? Versus G. They actually intersect above the x-axis. What's true about F versus G that would make him go first? Here's F. If I go underneath F, now I'm just joining the two together. I don't need them to be separate. Yeah, the area is larger. And so what's going to be true if I subtract a larger area minus a smaller area? Exactly. Area between, I need it. Whenever they're asking for area between, I'm looking for it to be positive. So this is not like integrals that are finding displacements and seeing if it's like a negative or a positive. Did it land to the left or the right or below or above? I'm not doing like a direction sort of thing with positive or negative. I'm just caring about like the geometry, the area. Area as a geometric measurement is always positive. So to make it always positive, I just need the bigger one minus the smaller one. And that's hopefully exactly what you're going to see in your forever card. That's hopefully exactly what you're going to see in your forever card. Now, we're going to be getting to our forever card in just 1 second, but I'm just showing it to you now. Do you see then why I say we need the top curve minus the bottom curve? If we do the top curve minus the bottom curve, I'm saying do the bigger one minus the smaller one, and the bigger one minus the smaller one is going to be positive. And if you don't know who's who, what's our fail-safe?
Bigger minus.
Well, we want the bigger minus the smaller, and if we don't know what's what, if we don't have a picture, and if we don't know who's who, we'll just throw in absolute values and be like, I don't know, just make it positive and it'll be okay. So we have a fail-safe that'll be coming. We can use absolute value, but we have a fail-safe. We can use absolute value if we don't know. But if we do know, if we can see it, we're going to pick the bigger one minus the smaller one, which will be the top guy minus the bottom guy. Or if it's oriented differently with y's instead of x's, it'll be the right guy minus the left guy. So our steps are actually fairly basic. The hardest part's going to be doing the integral after you set it up, but the setting up is important. So we have to figure out, unless we're using absolute values, we want to know who's bigger. We want to know who would make the bigger area so that we get a positive number. Then we figure out whether we're having natural or defined bounds. And then we just have to keep an eye open for splitting up integrals if curves ever switch orders. So this is just checking intersections. I don't want to get this too bogged down, so I'm just going to kind of leave it at these steps, and let's go play with examples, and we'll get our forever card in the midst of it. But guys, this is the idea of the entire section. But it forms the foundation for what's coming next. Go ahead and give me a quick, like, how many minutes you need to write the steps down, though. I don't want to, like, go ahead of you and overwhelm you. Okay. 2 or 3 minutes. As you guys are doing that, would it be overwhelming if I just check for intersections, if I do some pre-cal? I'm just going to do some pre-cal as you guys are writing down the steps, okay? That's all I'm doing. I'm just going to do some pre-cal over here. Just don't mind me just doing some pre-cal. Nothing to stress about. As some of you guys are finishing up writing, quick question, what pre-cal did I do? Catch me up, well, catch the class up on what I did. Set the functions equal to each other. Then what? Got them all on one side because I wanted to do what? Factor. Factoring, I set each factor equal to 0 and I ended up with 0 and 1. When I was trying to take them to a graph, or to the graph, what did I need to do? Plug in the points, yeah. So I plugged in 0, figured out what was going on, plugged in 1. I could have done it to both functions, but they have the same points, so it doesn't really matter. So now, what am I left with needing to figure out before I can just go for my integral? My integral right now, I know it's going to be between 0 and 1, because they didn't tell me anything different, so I'm like, all right, whatever, I'll use the natural ones. They're right there. Where they intersect? Oh, I already know that, though, because that's what this tells me. So I know they're intersecting, I know they're sharing these 2 points of 0, 0, and 1, 1. If you want to have that solidified just for this one example, remember I could also have plugged it into G, and the whole point of intersection is it's the exact same thing in both. So 0, 0, and 1 cubed. They're the same thing in both. Oh, set each equal to 0. So I set x squared equal to 0 and x minus 1 equal to 0. So square rooting 0 plus or minus 0 is just 0, and then adding 1 to the other side. X is equal to 1. Well, then I just plugged it into the function to figure out those are x's, I wanted the y's. Does that make sense? Yeah, I had the x's, I just needed the y's. So 0 squared, 1 squared just ends up being the same. Does that make sense? But hold on, what's my dilemma now? I need to know the bigger one versus the smaller one, so I subtract it in the right order, right? Or if you look forward at your forever card, I want the top minus the bottom or the right minus the left. No, that's when I'm doing y's. Everything's in terms of x, so I'm not doing y's this time, I'm doing dx. Could we stress out right now about which one's the top and which one's the bottom? We could get out our graphing calculator, we could talk about the points. But does anybody know what else we could just do? We could compare the powers and think of things like, I don't know, maybe like 1/2. Could we do something like that? Now that we know what it is, we could plug in 1/2. What's 1/2 squared? 1/4. So this guy is going to be plugging in like here-ish. What's 1/2 cubed? 1/8, right? So then 1/4, if I was to cut in half and cut in half again, I guess it'd be more like there-ish. 1/8 would be something more down here. Oh. So that's interesting. Who's going to be on top? Yeah. Cube doesn't get bigger until after 1. Cube doesn't get bigger until after 1. So x squared is actually going to be the top. But here's the question. What if you just said, screw it, I'm going to subtract?
Absolute value.
Exactly. If you didn't want to go to all that pressure or all that stress, we've already figured out our intersection points. So there's not going to be any weird like, hey, we have to split up. So we could actually just say, you know what? The tricky thing about handling absolute value in, oh, that's a forever card. Handling absolute value in integrals is splitting up at intersections. We already split up at the intersections. So the cool thing is from our earlier work in integration, we can just say this is going to be absolute value on the outside. We could put absolute value on the inside, but we already figured out our intersections. We can just put that absolute value on the outside and say, I just need to figure out what you are and make you positive. So if you had accidentally gone, this is the wrong way. This is bottom minus top because we actually got the picture. But if we went ahead and solved this, all that's going to end up happening when we solve is, well, 1/4 x to the 4th minus 1/3 x cubed. We have to anti-derive. We have to plug in our bounds of 0 and 1. And when we do that, we're going to have 1/4 minus 1/3 minus 0 minus 0. We're going to get some common denominators because that's what we do. We can multiply this guy by 3/3 and this guy by 4/4. We would end up with negative 1/12. And guess what would happen, guys, if we had just been right in our orientation all along? If we had switched it appropriately, we would have gotten the exact same number. It just would have been a positive 1/12. So as long as you've checked your intersections and you've split up the bounds appropriately, even if you get it wrong, all you have to do is just take the absolute value at the end, which would have been exactly what you would have found if you had just done it the right way to begin with. The right way, quote unquote. Yeah.
On the AP, are we gonna have to like anti-derive it by hand, or are we gonna have access to the calculator?
It depends on whether it's a calculator part or a non-calculator part. So the nice thing is for these questions for 6-1 and 6-2, sometimes on the AP, which you guys will see in like maybe the con practice, probably more in like a practice exam, the one that you get next week. No, we'll be working on that one together. And I'm playing with the idea, maybe I should make this your can to a drive contribution. I'm playing with the idea as long as you take the original mock AP, if you feel more prepared, if you're unhappy with that score and you want to try again of having like a take 2, on another practice exam like a week after we get back from spring break. I'm playing with that idea as well, which means a lot more grading for me, but I don't think everyone will take me up on it. Because some of you, you'll be fine with that grade, and it's more like you're just trying to get more and more prepared for the AP. But anyway, I want to take the pressure off as far as I want you to do your best on that day. I want us to get ready for that day, but I also want you to not think that that day is our final goal, because it's not. It's just one other day in the midst of all the preparation that we're doing. Kind of like our forever quiz is how you can take another one. This would just be a bigger commitment as far as a whole other official one in one setting. But we'll talk about that one as everything gets closer. But Andy, what I was saying is those practice problems, some of them just say write but do not solve, which is gorgeous because then you just need to give them an integral. So sometimes you're solving all the way, but more often than not, you're just setting it up. Yeah, Ben.
How would knowing 112 help us define that x squared is greater? Like the big problem?
Well, the purpose of the question wasn't figuring out who's bigger. The purpose of the question was knowing the area between. But by us getting a negative 1/12 and having it split up between its intersections, we figured out that like we actually had the smaller one minus the bigger one. So we figured out what should have been first. Even if we didn't have the picture, that it should have been this guy and then it should have been the other guy. But what I was trying to show you was even if you get the orientation wrong, as long as you split up at any intersections, you will end up with the same answer. Just you will need to think absolute value at the end.
So technically we wouldn't even have to know whether it's...
Exactly.
So we could just go straight into the absolute value.
Exactly. And that will only get tricky if it's something where like they've given you an A and given you a B and there's an intersection in between, you need to split up. Otherwise you're not doing the absolute value accurately. Does that make sense? So whether you do it this way or that way, this way will get you to the positive 1/12. This way you would end up at a negative 1/12, and it's like, no, we need it to be always positive. So we would go ahead and flip the absolute value. So is the picture crucial? No. But are you at least able to visualize this little tiny slice that's in between? Since we did draw the picture, I mean, yeah. So what if we were to take a second and write down the forever card? We didn't have a forever quiz last chapter because it was literally just one. I think it's up to you. What do you think Devon needs to wake up or not? I know he's had a hard week.
He's listening.
Oh, he is? Okay, as long as you're listening. I was just checking on him. We only had one card last time. It was just kind of summarizing the big ideas from that. So now we're on area between curves. For us, I believe, once again, remember these cards are one off. For us, it's 43. We're so close to being done.
How many forever?
As far as like the new content, we only have 3 more. I know, 6.2, remember I said it's hefty, which is why we're splitting it up. And why we're not having that test. That's a better deal. I think the better deal is that you have a chance for a makeup mock. As long as you attempt the first one. I think that's better for the canned food drive.
So if you don't turn in food, you don't get your extra thing?
I think that's what I'm thinking. Makes it well worth your while, and it's not bonus, so it's technically still meeting the department whatever policy. But that's why we're not going to have a test on chapter 6. Sorry, Sarah, just catching up. We're not having a test on chapter 6 before spring break. We're just finishing the sections, which is today, Friday, and Tuesday. And then we just get to like play with the practice exam next Thursday and Friday together. And then you'll have a WebAssign. You can work with people. You can access online resources, etc. over spring break. Just a WebAssign chapter 6 quest to kind of like solidify stuff over break. And hopefully that WebAssign quest grade will be a nice one too, since you're able to work with people and use online resources and things for everybody. As a nice last test grade. And canned food drive will get you an extra attempt on the mock. Okay. ones that are down below, I think are like the beginning of WebAssign. I don't want to totally take you guys away from this, but I do. Yeah, because WebAssign starts off with pictures. Okay, so I'm not going to leave it on there for long, but WebAssign starts off with pictures. Some of you might be in there, some of you will be in here at some point. WebAssign starts off with pictures. So that's why I've given those as our first two examples. But I actually have a nice screen for us to use on them. So I'm going to flip it over as soon as you guys have the forever card. Once again, the ideal is to have the top minus bottom, the right minus left. But in actuality, we just need to get a subtraction, absolute value to be safe in case we're wrong. But if we have the picture, we're going to make it right. And then split up at the bounds. Andy?
So is this one of those problems where you said like we wouldn't have to solve it all the way, just give them an integral?
Maybe not. I think in WebAssign, if we peek at it real fast, they actually, they just have you set up the integral. Nice. And this one, they just have you set up the integral, but they have you, no, just set it up. That one, you just sketch it. No, okay, now when there's a number, you're solving. Does that make sense? But then you guys all just saw 125 over 6, so if anybody memorized that, well, that's kind of nice. Okay, so let's go ahead and just set it up and see if we can figure out. Now, careful. Can we look at WebAssign for a second? Do you see any absolute value bars in what they're writing? Okay, why are they not showing you absolute value bars? Because you're being given pictures. Or you're shading, like catching the picture, seeing the picture. So they might not be having you do absolute value bars. The AP might not have you do absolute value bars in their answers because they're like, well, if we're asking you for it, we want it the right orientation. So be careful. For solving, absolute value keeps you honest. For matching to the right integral, well, the right integral would have the top minus the bottom or the right minus the left. So check it. Is this one a top minus bottom example or a right minus left example?
Oh wait, no. Top bottom, sorry.
Think about where your functions are. Let's talk about this, okay? A top minus bottom problem is going to be one where you have a dx. Versus a right minus left is going to be one where you have a dy. I know it's been a long time since we started integration, but there was that whole idea of you could go dx where we're using x's as our bounds, and we're doing the curve down. Then there were those weird ones that were flipped on the side, and we were using the y's. I remember Josh was asking me a question. I brought it up in class. Like the y's were the weird pictures that were flipped, and we were going the other way. dx's say top minus bottom. dy's say right minus left. What do you notice about the difference in what's given here versus what's given here? Do you see it? What are we in terms of here? We're in terms of f as a function of x, and then over here we're in terms of, no, we're in terms of f of x would be over here. So this would be like an f of x. This would be like a g of x. So we're in terms of x's over here. What are we in terms of over here? F of y, because it's in terms of y as my independent, and g of y. So that kind of helps. And can you guys literally see, like, the blue curve is always on top, the green curve is always on bottom, right? For any representative slice, I'm just showing a representative little baby slice. It would technically be a rectangle, and then it would be going all the way down to the curve, etc. But if I was just trying to plug this in, square root of x, my axes disappeared. I'm sorry, guys. These were my axes. There we go. This picture is being given to us. We wouldn't go setting these equal to each other because we can see it on the picture. Question, what are our x bounds? Think about what's on the x-axis. What's the farthest left x and the farthest right x for this picture? 0 is the farthest left, and then what's the farthest right? 4. It's probably easier if you're looking on your Jamboard. It's a little bit hard up here. So 1 and 2 and 3, and it's the 4th tick mark. So according to our picture, we're going from 0 to 4, and we're going to get our top minus bottom. So who's on top for this guy? Square root of x. And who's on bottom for this negative 1/4. So minus a negative would end up being a positive, right? I'm assuming we could make that match. So what's different with this guy over here? It's in terms of y. So I'm not looking for x's anymore. What am I looking to put in my integral? Y's. And did you look at your forever card, or do you need to? Instead of top minus bottom, I'm thinking right is more positive, left is more negative, so I'm doing right. What's further that way minus what's on this side? What's my bottom y value? Now we're going this way. It could be negative 1, except that's not shaded. So even though this would end up intersecting down here, since they gave us this picture, we're only doing this, so the bottom would be 0. Oh, got you. Remember, we have to look at the y's. So think about the y-axis. Over here, we were looking at the x-axis, 0 to 4. But now we're looking at 0 to, uh-oh. Who's that top dude? Is this defined or is it natural? The tick marks aren't super clear, right? Like, that's a 2, but I don't know exactly what that... So don't go guessing. Instead, it's natural because what's happening at this point, guys? Intersection. Okay, so just think, intersections, where they come together, what do we do with the equations? We set them... Okay. So let's do that for a second, because we need that... This is pre-calc. Don't stress. Pre-calc. We got this. We just need to set them equal to each other. So 2 minus y squared is equal to negative y. Oh, just negative y, I guess. The x would equal to x, so I set those equations equal to each other. Remind me what I did in the pre-cal a second ago. I set them equal, and then what did I do? I moved them all to one side for the purpose of trying to... Starts with an F and ends with an actor. So then I have 0 is equal to y squared minus y minus 2. Is that something I can factor? What multiplies to be negative 2 and adds to be negative 1? That's negative 2 and 1, right?
Wait, where did you get the 2 minus y squared?
Oh, because I subtracted the 2 and added the y squared.
Oh, because you said it equal to each other.
Yeah. Set that guy equal to that guy, and I moved it all. I don't like negative squares.
Wait, what was the method you did for like the x thing? For factoring?
There's a few different methods for doing this. One is you're trying to think about what makes y squared. And negative 2, you can think of like all the factors of negative 2, and it's like, well, 1 and 2, but what will add to be? This is just a way of organizing what multiplies to be that and adds to be that. So I'm looking at my last term, and I'm looking at my middle term. And so what factors? Well, I wanted those two factors. It's the only factors I had, and I needed it to add to be negative 1. It's just a factoring method. You could have also thought it's y and 2 and 1, and then tested 2y and 1y makes 3y. No. 2y minus 1y, no. Negative 2y plus 1y, that's what works. That's called the guess and check method. This one was... It shows a little bit clearer. This is the only way that I'll get my negative y. And then I can get my y minus 2 and my y plus 1. But anyway, there's a few different factoring methods.
How would you know which one of those two values to use? Since you got 2.
Oh, hold on, I went too far. Do you mean like in one of the factoring things I just did?
Yeah, because you got y minus 1, y plus 1. So which one of those two should you use? Or would you just put like 1 comma 2 or negative 1 comma 2?
Oh, they're both they're both intersections. So when I get back to my graph, let's look at what makes sense. Because as you just said, when we solve both of those, we get y is equal to negative 1 and 2. But I only need one of those. So it's like, oh, hey, it would intersect at negative 1. But like we said, that's not a part of this figure. 2 is. So I use the 2 because that's the only one that makes sense based on what they gave me. So they're both intersections though, right? Because negative 1 would be an intersection if I kept going.
Oh, yeah.
But they shaded here up.
Okay.
So I'm using the one that applies to my part of the picture. If they had given me the whole thing, I would have used negative 1, 2, 2, but they didn't give me that. So I said, okay, fine, you only want part of it, so I'm just starting at 0, not negative 1, going to 2. Oh, okay, and then who's on the right? In my figure. F of y? Yeah, f of y is on the right. So if I was to do the area, now this would be a little bit different, right? If I'm doing dy, I'm not going area down, I'm going area over. So f of y would get me this. Well, that's not enough. Minus g of y. G of y would be a negative because it's underneath, but minus a negative will add it. And I'll get everything I need. This is a little bit different in the sense of doing f of y doesn't go down, it goes over because it's dy. It doesn't get me enough. G of y would get me what I need, but it's negative, so I subtract. Nice thing is my formula still works. If I subtract a negative, I'm going to add and get exactly what I need. So I'm going to throw in my 2 minus y squared minus a negative y, which ends up adding it. I'm going to go ahead and just leave that minus a negative so you guys can see all the math that was done. And I've got them. Now, could I be needing to continue solving? Yes, but as we looked at in WebAssign, sometimes you're just setting up the integrals. And so we're just practicing setting up. Solving the integrals is something that would be review using FTC, anti-deriving, and plugging in bounds. Andy.
So really all the math we did was just to find the bound.
Mm-hmm. And then like setting it up appropriately, knowing what was going on. And even just using an integral in the first place, right? So I have one more example, and then we were just going to go to WebAssign. Does that sound good? One more example, and then I think we'll have 15 minutes in WebAssign. So I gave you a picture for this one. Once again, I didn't have to, but I did. I've gone ahead and used things like y equals mx plus b. To graph this guy at 1, 2, 3, 4. To graph this guy at an intercept of negative 4 and a rise over 1 of up to, over 1, up to, over 1, etc. So I could have graphed this guy. Theoretically, you could have graphed this guy without seeing it up here. Y squared, ew, it's one of those conic section dudes from last year. Where the y is squared, it's a sideways parabola. Okay, whatever. The vertex is y minus 0, x minus 0. The vertex is at 0, 0. And then we could plug in something like plugging in 1. Plugging in 1 would get me to 1, 2, 3, 4. It would get me to negative 4-ish. Yikes, it does not look like negative 4. Anyway, pretend that was actually an accurate graph. But guys, why do I have the word intersections over to the left? What am I saying what we need to do? Yeah. Because what did they not give me?
Intersections.
They didn't give me any clear intersections. So we're going to try and do this problem two different ways because this is kind of ambiguous. It's like, is it a top minus a bottom? Is it a right minus a left? I mean, this one has the y not by itself, and that one does have the y by itself. So it's like, well, let's talk about it. Let's end here. If we were doing it dx and if we were doing it dy, what would be different? Nope, that's a dy.
What's WRT?
With respect to. Sorry, it's a mathematical abbreviation. With respect to. With respect to.
I see an X.
What? Do you see something else?
No.
Oh. It's not another one of those Detroit things, is it?
No.
Okay. With respect to x, with respect to y. If I wanted to go with respect to x, first of all, well, I need intersections either way. And the picture isn't super clear. Like, I don't really have tick marks with the x's, and I don't really have them with the y's. So I'm going to have to set them equal to each other. But guys, I can't just set 4x equal to 2x minus 4, because that's a y and that's a y squared.
Square roots of 11. Oh my gosh. Yeah.
I could square root,
Nice.
but if I square root, who wants to set a square root equal to something? Does anybody see anything easier that we could set equal to? Or solve for to then set equal to? Yeah, they both have an x in common. So what if we were to get x by itself? Just in theory. X, this is easy, right? Y squared over 4, just divide. And then this one, x would equal, I need a little bit more math, but y plus 4 over 2. P.S. I just got my two equations that I could use with respect to y. That'd be kind of nice. I just have my two equations. But I can also just set them really easily equal to each other, because over here I can say y squared over 4 is equal to y plus 4 over 2. I can do some math now, like, I don't know, times 4 on both sides. I'm just trying to get rid of my fractions. I don't like fractions. So multiplying by 4 gets rid of that guy. I can do some math here. I'll have y squared is equal to 2y plus 8. What am I going to do?
Miss, how come the x equals are your with respect to y?
Because if x is by itself, isn't normally y by itself? Y is equal to f of x. If x is by itself, then that's going to be an f of y. It's kind of like inverse functions where everything is switched. But what I mean by in terms of y is it has all the y's inside. Do you know what I mean?
Yeah.
So I can say x equals, plug in the y stuff, plug in the y stuff. That's what I mean by with respect to y. Y is the independent variable. You guys know what I'm doing, right? Moving it all to one side? Doing a little X method is one way of organizing. You can also just think of your parentheses. It is going to be a y and a y. There's no tricky number in front. One way of organizing, though, is what multiplies to be -8 and adds to be -2. A 4 and a 2 with a -4. And I get y equals -2 and 4. So now I know exactly where this is hitting. This is hitting at -2 down here, and it's hitting at, ooh, my tick marks are not very accurate up here. Anyway. It's hitting at -2 and 4 according to the math. Now if I wanted those actual points, I could do some plugging and chugging. In the sense of I could plug in -2 and say, what is f of -2? That'd be 4 over 4, which is 1. And what is f of 4, which would be 16 over 4, which is 4. So I can have 1, -2. Now all of a sudden, I know my bounds either way. My bounds are either going to be x's or my bounds are going to be y's. My bounds are either going to be x's or my bounds are going to be in terms of y, it's already gorgeous and ready to go, so I would just use the guy on the right, which is green, so y plus 4 over 2, minus the guy on the left, which would be blue, which is y squared over 4. If I was doing with respect to x, things get really, 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 really dicey, because I actually have something really weird happen. If I was to look at the top minus the bottom, anywhere after the intersection point, it's clearly blue and green. The problem is that's not all there is to this problem. If I just do top minus bottom, blue minus green, first of all, I would need to do what Josh already said, which is I would need to square root both sides, and so y would equal a plus or minus square root. I have a top and a bottom curve. So the blue is actually the positive square root of 4x, which is still, I guess I could say, 2 root x. The bottom is the negative square root of 4x. So actually, this blue curve is really just the positive square root minus the green curve is 2x minus 4. Careful, don't kill a seal. Got to get that subtraction in there. But that actually wouldn't solve for everything. That would only solve for a part of the area. If I wanted the rest of the area, I have a missing little slice over here at the very beginning where I would actually have the parabola going to the parabola. And to get that, because I need to get all the way back to x equals 0, there's some stuff going on at x equals 0. I would actually have to add from 0 to 1 of the top square root minus the negative square root, which ends up just being double whatever I've got going on, because I'm adding it. Man, which one is so much easier in this case?
Why?
How come? There was one clear y bottom, one clear y top, and I could go ahead and plug it in. For the x's, I had the x of the intersection coming halfway into or partway into the figure. And to get the whole thing, I would have to backtrack and get this other stuff. Yikes. That was dicey. Yeah.
How did you get your 1 and 4 again? Like, what did you plug into?
Oh, the x's. Because I needed x bounds if I was doing dx. So I used the x's of my intersections, and I got those, Andy, by plugging into my function. So I took my y of negative 2 and I plugged in. And then I took my 4 and plugged in. 16 over 4 is 4. Yeah. Lucas.
Do you think there will be a problem in the AP where we have to?
You won't have to do it the messy way, but if you have a choice and you just naturally revert to 1, I just need you to realize what top minus bottom means. It means the top minus bottom of the entire figure, which might change at some point, because it was blue and green, blue and green, blue and green. Oh no, it's blue and blue.
And then,
Right.
No, go ahead.
How come you have to add from 0, the integral from 0 to 1 again?
Yeah, can you, not sure, can I do this? Okay, Andy, do you see how top minus bottom, right? If I was to draw any slice down to the x, I just budged it a little bit. There we go. It's blue and green, right? Top minus bottom, blue, green, blue, green, blue, green.
Yeah.
All the way up until this point. Then all of a sudden, to keep going, there we go. It's blue, green until here, and then all of a sudden, what's top minus bottom? Blue, blue. You see it? So to get all the way here, it's blue, 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 blue. Oh, blue, green, blue, green, blue, green, blue, green. So I needed to get from 1 to 4, that's the red. From 1 to 4, it's blue and green. But there was area before 1, starting at 0. From 0 to 1, it's blue, blue. So I needed to go ahead and say, oh, the blue-green from 1 to 4 isn't enough. There we go. The blue-green from 1 to 4 isn't enough. There was a little bit of area back here from 0 to 1, which made the right minus left so much better. Because what's always on the right? Always, 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 always. Green, blue, green, blue, green, blue. And that's the entire figure. So that's what makes this the preferred way of solving.
So, Misty, how come it's a minus at that point? Wouldn't you be adding the area at the top and the area at the bottom?
But the minus is what's happening. Bummer. The minus is what's happening in the integral itself. So this guy would be, let's see. This one was specifically talking about, what did I make it over there, red?
No, not for that. For that one, I understand. Like, it has to be minus because you're subtracting the area of the green to the x-axis, but for the second part, for the blue to blue.
Oh, because this area is a negative, so I need to subtract the negative to add it. The area is below, yeah, so it would be a negative area, so subtracting the negative will add that area to make it like area plus area equals the whole. And
So then, how come that area is blue and it's not all blue green? Like, why is it just one color rather than the whole that area being super cool? Because it changes sign.
I'm shading stuff. Whereas this one is because it's all in how you're looking at it. If you're looking at it in terms of y, I'm looking across. And looking across, I always have a solid right boundary and a solid left boundary because in terms of y, I can have the whole parabola. In terms of x, I have to split it up to get the whole parabola. So I actually, in terms of x, I have 1, 2, 3 different curves. In terms of y, I only have 2 different curves. Because of this little thing called the vertical line test that says, uh-oh, you can't have one on top of the other. It's impossible. I don't have a way of showing it without a plus or minus. So in terms of x, it's like, okay, here's one piece. Here's another piece. Here's another piece. And so that gives me this necessity of having like, well, one boundary is that guy, another boundary is that guy. And then that moves until here, and then all of a sudden it changes. As opposed to just saying like, here's one piece and here's one piece. That's what, in terms of y, lets me do. It lets me see the right, see the left. As opposed to x, it's like, oh, there's a top, there's a bottom. That gets real awkward. I don't know if that answers your question. But it's all in how you're looking at it. If you're looking at it top, bottom, this gets messy because it's a straight up and down line. If you're looking right, left, I'm looking at a horizontal line instead, which allows us to do it much simpler. Kiddos, I meant for us to go to WebAssign next. Maybe some of you guys are already in WebAssign. Sorry, I know that was a tricky one as far as conceptually. I meant to be like, yeah, go on WebAssign. Those of you that are in WebAssign, do you have a problem that we could throw up and just do a homework problem? Here at the end, have you found anything tricky? So then maybe I'll just go to number 5 since no one found another specific one necessarily, because this says with respect to x and with respect to y, so it's like the tricky one that we just did. So I'll see if I can just help you set this up, because it's like the tricky one that we just did, and I wouldn't want you guys to agonize over this on your own. So if we were thinking about this with respect to x, if we're thinking about this with respect to x, first of all, we would want to think intersections. So intersections, we would come over here off to the side. This one is going to be my line just based on degrees. This one is going to be my parabola. So actually plugging into my integral makes this one really nice and easy. Because I see that the line is always on top, so I can do 6 minus x minus my x squared. That part's nice and easy. But as far as my x bounds, like, I don't know, those are kind of like an awkward spot. So we would go ahead and do that, setting equal to each other, getting it all to one side. Seeing if we can get some factors. So x is equal to negative 3 and 2. So I can throw in my bounds of negative 3 and 2. We can either plug that into our graphing utility as an integral, use our calculator, change it to a fraction, we would get 125 over 6. This one, top minus bottom, is clear the whole time. Any way I slice straight up and down, the line is on top of the parabola. So this one, dx, is the clear choice. The dy would be the messy one. You could still do it, it would just be messy. I would want to plug in my f of negative 3 to figure out my y's, and my f of 2. I would end up with 9 and 4. So I would have 2, 4, negative 3, 9. But if you guys notice if I was to slice this, I have the line on the right and the sideways parabola or the left parabola on the left, but over here I would have from parabola to parabola, and this is where it would get dicey because in terms of y I would have the positive square root of y to the right and the negative square root of y to the left if I solve for x. And then this line I would have x is equal to 6 minus y. So I would need to do this really funky adding thing. This really funky adding thing where I can go from 4 to 9. I can go with my y values, but what about all the stuff going on between 0 to 4? From 0 to 4, I have parabola to parabola, so I would have this minus the negative this. But then I could use my line of 6 minus y minus my negative. And if you guys throw this into your graphing calculator, this addition would be the same as that one. It's crazy. It's kind of mind-boggling. But it finds the same area, just a weird way. Sorry, guys. You can go ahead and get out of here. Great job, and I hope I helped you on like what I think is probably the trickiest problem of homework.
So it's always A and B are the same.
Oh, practice test. If you guys have them, it's due by 3:30. Or by the time I leave today, if you're on the normal schedule. Which of you guys took pictures? You're like, I'm available to tutor for those kids that are behind. Josh, Andy, Lucas, Noah are all available to help on this take-home portion. Just reach out. They would love to help. Any more take-home portions today? I'll do note checks and spiral checks. If you guys can bring them, that'd be great. But I can always do that. Oh.